So in this section, we're going to continue this idea of line integrals, but we're going to talk about another way that we can potentially evaluate them. So you can see in some of our other examples, if we kind of have piecewise curves that we're going over, it can be really tedious to evaluate each and every one of those boundaries. So one of our next theorems is going to help us figure out a different way to evaluate these, but it only works in certain circumstances. So this is called Green's theorem. So what I'm going to do is state it and kind of give you the reasoning as to why. There is absolutely no way I could prove this in a very short time frame. So hopefully the reasoning itself makes sense as to why this is true. So Green's theorem states, let C be a piecewise smooth single closed curve with counterclockwise orientation. That encloses a region R in R2. Okay. So all we've done so far is we've kind of seen like it starts at one point and ends at another. But here, this key stipulation is it's a closed curve. So the starting and ending point are going to be exactly the same. The orientation is also important. In most of our math, we use counterclockwise. Okay. If it's not counterclockwise, well, remember, if you traverse it in the different direction, you just negate the sign. So all you would have to do is do the opposite sign for this. So what we can do, instead of evaluating on the boundary, I can instead be concerned with the region that it encloses. So if the vector field inside of our line integral has those components P and Q, where these have continuous partial derivatives, in an open region containing R. Then we can do the following. So if I want to evaluate the line integral over this curve C of this vector field dot dr, to indicate that this is a closed curve, what we do is we put a circle on the integral. So this means the curve is closed. To just kind of give you a visual of what that looks like then is your curve forms a nice region and it has that counterclockwise orientation. So this is the region that it encloses in the XY plane. Instead of evaluating this along the boundary, I can instead focus on this area that's on the inside. So we can instead turn this into a double integral where the bounds depend on the region we integrate, or we're finding this over, that C encloses. And then on the inside, we're going to have qx minus py. So remember, those represent the partial derivatives of q with respect to x and p with respect to y. And then we integrate this with respect to x and y. Okay? So the quickest intuitive explanation I have deals with what these things represent physically. So remember when we were working with line integrals, I mentioned that it represents the amount of work you would do to walk along this curve in that direction, in that vector field. And that is one application of it. But the other thing, remember, these vector fields represent fluid flow also. We talked about them being representative of like a river, and that's your tendency to move around that point. So another thing that these line integrals calculate is the tendency of the fluid to move. So essentially what would happen here in a closed integral or a closed curve is this line integral would tell us how much the water is going to circulate around this path in this particular direction. So instead of doing that on the boundary, it's also related to the tendency of the fluid to rotate inside that region. So that's exactly what this is calculating. It ends up actually being a concept called curl, which we're going to get to in the next section, but it's the tendency of the fluid to rotate in that particular point. So we already talked about types of vector fields, and we had that rotational vector field. That's something that has curl to it because you're likely to continue to move in that path. So that's just one quick kind of explanation as to why these are true. Again, you can look up a proof online. It is quite intensive, so it will take you a bit of time, but you can also think of it as vector flow. So the tendency of the fluid to move around that path in this closed curve is also related to the tendency of it to rotate inside this region, okay? So what I'm going to do is I'm also going to give you another alternate notation for this based on this initial piece. So it depends on the problem or really the field that you're working in as to which notations are commonly used. But if you're calculating this line integral over a closed curve C of f dot dr, we can instead replace f by exactly these functions p and q. And then dr, remember, is dx dy. So another way you can also see this represented in a single integral is you have the first component times dx plus the second component dy. So you'll often see it in this form. I'll show you instead how you go about that, because realistically you want to just transfer it back to this original to find your vector field and then go ahead and calculate it. So what I want to do is I want to first show you that this is accurate by doing these line integrals by parametrizing the boundary. And then we're going to see the beauty of using Green's theorem and how much quicker it can tend to be. So the first example we're going to work with is a semicircle. So we're going to evaluate the line integral over the closed curve C of f dot dr, where f is the vector field 1y, and C is the piecewise curve that encloses the region bounded by x squared plus y squared equals 1 above the x-axis with counterclockwise orientation. And remember, if it gives you clockwise orientation, all you would do is pop a minus sign out front of this, because this works for counterclockwise. But if you traverse it in the opposite direction, it still gives you the same value, just opposite signs. So we're going to do this two ways. First, without using Green's theorem. This is actually going to be a really nice example because we're going to do this using line integrals, using Green's theorem. And then realistically, this ends up actually being a conservative vector field. So we'll see that when we get to using Green's theorem. So we'll get some practice with that fundamental theorem for line integrals as well to kind of just show you this doesn't contradict anything we've done yet. So first and foremost, what I'm going to do is I'm going to go ahead and sketch this region. So it's above the x-axis, and I'm working with a circle of radius 1. So it ends up actually being a semicircle. So here is my circle of radius 1 above the x-axis, and they tell me it encloses the region, so it also includes that component of the x-axis. So I end up going counterclockwise around this, and if I want to evaluate this using line integrals, I have this curve C1, which is the semicircle, x squared plus y squared equals 1. And then I've got this bottom part, C2, which is where our y is equal to 0. So to evaluate the line integral over this closed curve, what I need to do is first find the line integral over C1, and then that's going to have its own vector function to parameterize that. And then I'm going to add the result from using C2, which will have a different vector function parameterizing it. So I've got to calculate two separate line integrals and then add them together. Okay. So starting with C1, because that is the more complicated of the two. Okay. In this case, I want a semicircle. The best way I can parameterize that is using cosine of t, sine of t, because I do have to go in counterclockwise orientation. And then I only want this top half, so my t value is going to range from 0 to pi. Okay. Then I definitely need to take this derivative, which results in negative sine of t, positive cosine of t. My vector field F is 1y. So if I evaluate this along my curve, 1 does nothing, but my y value is sine of t. So this gives me 1 sine of t. Okay. So to calculate the line integral along this first curve, what I need to do is I need to integrate this from 0 to pi, and I'm going to take my vector field along this curve and dot product it with r1 prime, and then integrate with respect to t. So this becomes the integral from 0 to pi. This first component is 1 sine of t, and then this is negative sine of t cosine of t. Okay. So not a terrible dot product. This gives us from 0 to pi. Then going through each of these, 1 times negative sine of t gives me negative sine of t. And then I go ahead and do the same thing with the second component. Sine times cosine is exactly that. Just leave it as sine of t cosine of t. Okay. First one thankfully has a very nice antiderivative. Antiderivative of negative sine is positive cosine of t. Now over here you'd have to make a u sub, so you can do that off to the side if you want, if you're comfortable just saying what that is. If you want to integrate sine of t cosine of t, you can let u be either one, but sine of t is definitely easier because then you don't have a minus sign. So du is positive cosine of t dt. So this ends up equaling the integral of u du. which is 1/2 u squared plus c. So plugging in u, the antiderivative of this would be 1/2 sine squared of t. And then we're going to evaluate this from 0 to pi. So if I plug in pi, cosine of pi is -1, and then sine of pi is 0. And then I subtract, plugging in 0. Cosine of 0 is 1, and sine of 0 is 0. So this ends up equaling -2. Okay? So we've got our first line integral done. Now I need to go through the second one, which is just along that x-axis. So my second integral is along C2. In this case, since I'm just on the x-axis, the vector function we can use here is t, and the y component is 0. And then our t is ranging from -1 to +1. Because again, the orientation matters. In this case, to get that counterclockwise, I traverse it in this direction. So this one's a little bit nicer than our other lines have been. So we've got our vector function. So its derivative is fantastic. It's just 1, 0. Remember, our vector field is 1y. And so when I evaluate this along the curve, my y is 0, which is beautiful. So the line integral over C2 of f dot dr2 ends up becoming an integral dealing with t. So my t bounds are -1 to 1 in this case. And then I go ahead and take f evaluated along R2, dot product it with R2 prime, and then integrate with respect to t. So just to show you what each of these are, this is f along R2 of t, and then this is R2 prime. So even better, this is -1 to 1. When you go ahead and multiply these like pieces, this gives you 1 plus 0. So this ends up just being 1 on the inside, which is amazing. The antiderivative is t, evaluated from -1 to 1. So you get 1 minus -1. This is equal to 2. So finally, I've done the work to find the line integral along this closed curve. It's equal to the line integral along C1 plus the line integral along C2. And you notice I'm not using the closed curves for these because C1 and C2 are not closed. The first one we found to be -2. This one is +2. So overall, this thing is equal to 0. Okay? So a lot of work to get to this point. So let's try this now using Green's theorem. Okay. So what I'm going to do, because this is a closed curve, is we're going to turn this into a double integral over some region. And then you have qx minus py. Okay. So I'm going to redraw my region in the xy plane here, just to make life a little bit easier so we don't have to keep scrolling up. Here's the top half of that circle. It's got counterclockwise orientation, so I don't have to worry about that. Okay, and so the region that I'm working with is this one here that it encloses. So these are going to determine my bounds. Okay. And then I'm going to use my vector field to go ahead and find these components. So you can absolutely set up these bounds. In this case, you would have to figure it out going from dy dx or dx dy. In this case, the top half here would be the function 1 minus x squared under a square root. So your y bound would go from 0 to this, and then your x changes from -1 to +1. But we're not even going to have to do that because the vector field we're working with is again 1y. The first component is the function p, the second is the component q. So the function p is 1, the function q is y. And just like when we were finding conservative vector fields, all I'm going to do is take the partial derivative with respect to the opposite variable. So p is in the first component, I differentiate this with respect to y. Q is in the second, so I differentiate this with respect to x. Okay. So the partial of 1 with respect to y is 0. The partial of q with respect to x is 0. So because these two end up being exactly the same, this tells me my vector field is conservative. So realistically, I can use the fundamental theorem for line integrals on this. I didn't even need to do what I did in part A. We could directly go into finding a potential function. But honestly, Green's theorem is even easier for this because I have this closed curve. So the inside functions here end up being 0 minus 0. I'm doing a double integral over nothing. Okay. So this line integral turns into this double integral. I don't even need to write the bounds because qx is 0, qy, or py is 0. So you're finding an integral over nothing. This is nothing, okay? Which is exactly what we got in the regular sense of doing this without using Green's theorem. But it took us almost no work to go about this. So we still end up with exactly the same answer, which is fantastic. Okay, so see, this takes 3 lines or 5 lines, whatever this is, versus going through 2 separate line integrals. Okay, but what I want to show you is, because again, I didn't get to do a ton of examples in my line integral video or my fundamental theorem of line integrals with finding that potential function. I want to show you how to do that. But realistically, I still don't even need to do that because if you think about the fundamental theorem of line integrals, all that matters is your starting and ending point. You can honestly pick it to be any of these because it's a closed curve. Since the starting and ending point are the same, when you subtract the function of those values, you end up with nothing. So when you have a closed curve in a conservative vector field, that line integral is always going to equal 0. Because at some points, basically, you've had to maybe work against the vector field or against the wind, but in other directions, it pushed you, so it gave you a little bit of energy. So you're not going to waste any energy walking along this path, okay? But again, just for some practice to kind of tie all of these components together and show you that everything is working, I'm going to go ahead and find this potential function and basically write down everything I just explained. So this last example agrees with the fundamental theorem for line integrals. I'm not writing all that out. So fundamental theorem for line integrals. Since this vector field f, which is given by 1y, is conservative, there exists a potential function little f such that this vector field is exactly the gradient vector of this function. So the first component is the partial with respect to x. The second is the partial with respect to y. So I'm going to go ahead and find this potential function. So ultimately, our vector field is 1y. That tells me the first component is the partial with respect to x. The second is the partial with respect to y. So partial of f with respect to x is 1. Partial with respect to y is y. Okay. So what I want to do is I want to go ahead and I want to integrate this to undo this partial derivative. So my function is going to be the integral of the partial with respect to x with respect to x. So we're going to integrate 1 with respect to x, which just gives us x. Okay. But again, normally you get a plus c, but in this case, because I'm dealing with a multivariable function and I integrated with respect to x, in turn, I really end up with a function of y. Because reversing the process, if I differentiate this with respect to x, that gives me 1. This piece gives me 0. So I end up with still the same piece here. Okay. So currently, as my function stands, it's x plus h of y. Okay. So what I want to do is I've utilized this first piece. Now I need to utilize this other partial to try to figure out this function. So if I differentiate this with respect to y, well, the derivative of x with respect to y is 0. The derivative of this with respect to y is h prime of y. Okay. Well, since I'm saying this is the partial with respect to y, this better equal this thing as well, because that is what the actual partial derivative is. So I set these two things equal to each other. And that tells me that h prime of y is y. So if I want to find h of y, I go ahead and integrate this with respect to y, which gives me 1/2 y squared. And now here is where I get that constant. Again, we don't use c because we use that to represent a curve, so we tack on a plus k here. Okay. So filling these pieces together, we know our function is equal to x plus h of y. We just figured out what that is. So the most general potential function is the following. It is x plus 1/2 y squared plus some constant k. And again, you can always check that you found the right thing, find the gradient of this. So the partial with respect to x is just going to be 1, and that's exactly what we have in the first piece. Then when I take the partial with respect to y, this is the only thing dealing with y. Its derivative then is 1/2 times 2, which is 1, and then y to the first. Exactly what we have in that second component. So when I'm using the fundamental theorem of line integrals, you get the freedom to pick the value of k. So I'm going to choose k to equal 0. So if we choose k equals 0, then that particular potential function is x plus 1/2 y squared. Okay. And the gradient of this is again exactly what we started with. So what I want is by the fundamental theorem of line integrals, we get the line integral over this curve C of f dot dr instead becomes the potential function, and I want to evaluate it at the initial and start, or the initial and terminal point. So just to refresh on our curve, it is this piece here. We didn't declare an initial and starting piece because it's a closed curve, so we'll say it's right here at the point 1, 0. So my starting point is 1, 0, but it's also my ending point. So honestly, regardless of this function for this conservative vector field, you have the same starting and ending point. This thing is equal to 0. Okay. So this shows you how to find that potential function, how to use Green's theorem, how to do just regular line integrals. So again, this is a very hefty problem. We're still going to do some more examples just using Green's theorem. But this just is another way to help us that if I have a conservative vector field, we know we can always do this potential function. But when I have a closed curve, I don't need to do that. The line integral is always going to equal 0. Okay. So in general, if f is conservative, and C is a piecewise smooth closed curve, then the line integral over that closed curve C of f dot dr is always going to equal 0, since the initial and terminal point are the same. Okay. So hopefully that's a decent refresher of everything going on. But again, we're going to do some more examples of Green's theorem. So let's try this next example. We're going to evaluate, that's not how you spell evaluate, the integral I, which is the line integral over the curve C. And we've got cosine of y dx plus x squared sine of y dy, where C is the boundary of the rectangle with vertices at 0, 0, 5, 0, 5, 2, and 0, 2, with counterclockwise orientation. Okay. First thing I'm going to do is I'm going to rewrite this because I don't particularly like this this notation. I think it's a little bit hard to read. You can directly pick out your vector field from this because this is just the first component. It's attached to x, and then this is the second component that's attached with y. But I think it's a little bit cleaner when I go to evaluate it to just have those pieces. So this integral I instead is just basically the dot product that's been expanded. So what I can do is write it as cosine of y and x squared sine of y dot product with dx dy. So the first piece is exactly the vector field we're working with, and then dx dy inside a vector is exactly dr. Okay. So here our vector field, f is given by cosine of y and x squared sine of y. So my function p is the first component, and my function q is the second. Immediately, because they already told me this is a line curve over a closed region, Green's theorem is likely going to be the better case. So I'm going to just go ahead and start, because again, if this is conservative vector field too, it's very useful to find that as well. So I might as well check if it's conservative. So if I take the partial of the first component with respect to y, this is negative sine of y, and then the partial of this with respect to x is 2x sine of y. So unfortunately, I can't apply the fundamental theorem of line integrals because these two things are not the same. But however, because again, I'm finding a closed region, Green's theorem is going to make sense. And this works out nicely because I've already then found what needs to go inside of the integral for Green's theorem. But here, since py is not the same as qx, we can't apply the fundamental theorem for line integrals. However, the region that they give us is a rectangle. And if I look at these points, my x goes out to 5 and my y goes out to 2. So plotting each of these, the vertices would be at 0, 0, 5, 0, 5, 2, and 0, 2. So we get this rectangle here, and it has counterclockwise orientation. So that means we're traveling along this path. So if I were not using Green's theorem, unfortunately, you have 4 line integrals to evaluate because each one of these would require a different vector function. So you'd have to find 4 different vector functions. You'd have to evaluate f along each and every one of those. They're going to have different bounds. It's not going to be fun to do. So without using Green's theorem, we would need to evaluate 4 different line integrals. But instead, because this encloses a region, I can deal with the rectangular region, which we know rectangular regions have the nicest bounds because they're just constant bounds. So instead, this is my region R. So by using Green's theorem, the integral I, which is the integral of the closed curve C of f dot dr, can instead be turned into a double integral over R, and on the inside it's qx minus py. integrated with respect to x and y. So we found those inside pieces already. Qx was 2x sine of y. And then py is negative sine of y. Oh, I need one extra parenthesis there. There we go. And then you can do whatever order you want, but dy dx is perfectly fine because, again, these are constant bounds. So thinking about the values of this, our y is changing from 0 to 2. And then thinking about x, the x is changing from 0 to 5. So we just need to evaluate this double integral. I'm going to clean it up a tiny bit. So the inside becomes 2x sine of y plus sine of y dy dx. And then you can go ahead and take this piece by piece. It's not bad to integrate with respect to y. But however, we can even take this a step further. These both have a sine and y in common. And that's the only thing that deals with y. So this is actually a separable integral. So we can say that this is sine of y times 2x plus 1. Okay. So instead of going one variable at a time, instead I can go from 0 to 5 of 2x plus 1 dx. And then go from 0 to 2 of sine of y dy. And so we'll go through the first one. The antiderivative of that would be x squared plus x, evaluated from 0 to 5. So plugging in 5 will give us 25 plus 5 minus 0. So the first integral becomes 30. Then I need to times it by whatever this ends up being. Antiderivative of sine of y is negative cosine of y, evaluated from 0 to 2, which gives me negative cosine of 2. No idea what that is. I have to leave that alone. And then minus cosine of 0, which is 1. So this ends up being 30, and then I'm going to rearrange that a bit, put the 1 first, and then minus cosine of 2. Okay. So again, a single double integral as opposed to dealing with 4 separate line integrals. But it only works because this is a closed region. Right? So let's do one last example. We're going to evaluate c, or the line integral over the closed curve c, of y cubed dx minus x cubed dy. Okay. Specifically, where c is the circle, x squared plus y squared equals 4 with clockwise orientation. So this one's slightly different because, again, it is clockwise orientation. But all that means is I get a minus sign out front of Green's theorem because Green's theorem is for counterclockwise. So I'm going to go ahead and prep everything first, and then we'll take care of that afterwards. So if I'm looking at this line integral, again, I don't like this form. So instead, I'm going to write this as y cubed and then negative x cubed dot product with dx dy. So I don't need to say this is f dot dr. Instead, immediately just say, okay, my vector field f is then y cubed negative x cubed. Okay. So the first component is p, the second component is q. I want to see if this is conservative because it's this closed curve anyway. If it's conservative, immediately I know this is equal to 0. And I need to go ahead and find these partials anyway to use Green's theorem. So derivative of the first component with respect to y is 3y squared. Derivative of the second component is negative 3x squared. So unfortunately, not conservative, but that's okay. All right. So the region that I'm working with is a circle of radius 2. So I'm going to draw my circle first because that's easier than filling in the pieces. Make it a little smaller. Okay, so this is 2, 2, negative 2, negative 2. And then my region R is the one inside of here. Okay. And this has clockwise orientation. So this is traced in the opposite direction. So starting out, using Green's theorem, this integral of y cubed dx minus x cubed dy can be turned into a double integral over the region R of qx minus py. But again, this would be for clockwise orientation, so I need to put a minus sign out front here. Because we have the opposite orientation of Green's theorem. Okay. So filling in these pieces, that is negative double integral over the region R. Qx is negative 3x squared minus py, which is negative 3y squared. And then to make my life easier, because I got a ton of minus signs going on in here, this is 3x squared plus 3y squared when you distribute that in. Okay. Now when I go to set this up, I can use x and y bounds. However, because I have a circular region, it's going to make sense to use polar. Okay. So our region R is a circle. Instead, let's utilize that. So I'm going to have to switch over this inside. I'm going to factor out that 3 to see I have the x squared plus y squared. Okay. So switching this over, I'll worry about the bounds in a second. X squared plus y squared becomes r squared. So the inside is 3r squared. And then remember when we switch over dA, we end up introducing an extra r. So this is r and then dr d theta. Thinking about my r bounds, this is a circle of radius 2. So r is going from 0 to 2. And I'm going fully around the circle. So this goes from 0 to 2 pi. So this becomes the double integral from 0 to 2 pi, then 0 to 2 of 3r cubed dr d theta. And then I don't have theta in here at all, so this is even separable in this case. It's the integral from 0 to 2 pi of d theta, and then from 0 to 2 of 3r cubed dr. First piece you've done, it's theta, then you evaluated those bounds. Again, I'm comfortable with you just saying, go ahead, that's 2 pi. And then the second piece, going through our power rule, this becomes 3r to the 4th over 4. And then we evaluate this from 0 to 2. So that's 2 pi. When you plug in 0, it'll be nothing. So this is 3 over 4. And then 2 to the 4th ends up being 16. So simplifying this a little bit, that gives me 4. So 4 times 3 is 12 times 2 in total gives me 24 pi. So again, hopefully you can see the benefit of this. It is much nicer than going through and evaluating the boundary of this, because the linear integral would be a whole bunch of cosines to powers, sines to powers, and then you have to multiply stuff together. It would not be pretty. So instead it turns into a very nice polar integral.